Hello, my name is Milan Knezevic and this video is my project assignment. Topic of this video is analysis of two improvement strategies for string searching algorithm using Burrows-Wheeler transformation and FM index. Assume you're familiar with this algorithm. If you're not, I will put a link in the description to a video lecture explaining the concepts of this algorithm. Before mentioned strategies have a goal to decrease memory consumption. The algorithm makes use of four data structures. First one is L, or last column, or Burrows-Wheeler transformation. It is, in theory, the size of the original text, but due to its heavily repetitive nature, it is a good candidate for most compression algorithms. Next one is F. F is compressed first column of the sorted suffix array. We only need to store an integer per distinct character of text. Suffix array tells us what rotation of the original text has been used to calculate a particular character in the last column. So we need to store an integer per rotation. And finally, tally. Tally informs us how many times have we come across a certain character. So we need to store per rotation, per distinct character, and integer. In reality, even more memory is necessary because of different implementation of these data structures in different programming languages. Suffix array and tally can be downsampled, and I will discuss how downsampling them impacts time and memory consumption. Testing data are sequences of nucleotides from 3 different chromosomes of different species. These sequences are matched against their respective patterns. This search is then executed for all combinations of suffix array and tally downsampling factors. Execution time and memory consumption are dependent on text and pattern lengths. By analyzing collected data, I have concluded that execution time is dependent on pattern length approximately in inverse linear fashion, and the dependency of memory consumption on text length is of linear fashion. In order to eliminate those dependencies, results are scaled. We then calculate average results for combination of factors. To get better understanding of results, memory consumption is converted to memory improvement ratio, showing us how much the combination of factors improve original algorithm memory consumption. And also execution time is converted to time increase, telling us how much the execution time get bigger than the original execution time. On this slide, we can see that with increase of suffix array downsampling factors, the increase of tally downsampling factors results in bigger memory improvement. On the other hand, on this slide, we can see time increase ratios, and the chart shows us that with increase of downsampling factors, execution time increases, but it increases slowly, which gives us a chance to find parameters that make bigger memory improvements, but don't add too much execution time. As I mentioned before, there is a trade-off between execution time and memory consumption. To find overall optimal combination of factors, results are normalized and their harmonic mean is calculated. This chart shows us that optimal parameters are 64 and 128 for suffix array and tally downsampling respectively. Optimal parameters give us 2.75 times bigger execution time and consume 53.92 times less memory. I would like to thank you for taking your time to watch this video. I hope you find this analysis interesting. The link to the GitHub repository of this project is in the description. Thank you and have a wonderful day.